All right, so let's just summarize what we're trying to do in chapter 38. We're looking at the evidence for the particle properties of electromagnetic waves. So in other words, evidence for the photon. Now recall that in Planck's assumption, we have energy is proportional to the frequency of the photon, and that's equal to hc over lambda. So that's the energy then of a photon that has a wavelength lambda. And so what we saw in the last lecture is that if the photon energies are in the range of visible light, or also infrared or ultraviolet would satisfy this as well, then the electron is able to literally absorb the photon. Okay, so it kind of swallows it, if you want to think of it that way, and the photon becomes part of the electron energy. So the photon as a particle does not exist after it's been absorbed by the electron, but the energy is conserved. And so this then is the whole idea behind the photoelectric effect. Now if we can look up on the data projector, we can see a device that is used to measure the energy of the electron. So we have a source of light coming in. This would be the metal here, and here would be the ejected electron. That would be measured by a collector here. And then a current could be measured for that, and that would then determine the number of electrons per second that are being evaporated off the metal. But to verify that the electrons have a certain kinetic energy associated with them, we can use a variable power supply, and we can use this to create a back EMF so that the electrons just stop hitting the collector plate when the back EMF is set to a certain value. So we can figure out then what the work function is from looking at the minimum frequency of light that will cause an electron to escape. But then we can get the kinetic energy by setting a back EMF. And since they're electrons, the number of electron volts is just the number of volts multiplied by the charge on an electron. And so that then gives us the, by knowing what the back voltage is that stops the current going to the collector, we can then figure out the maximum kinetic energy. And so this is the basis behind the lab exercise that you have for lab number 1 as a computer simulation. Okay, so that's the first kind of photon interaction with matter. Okay, so basically then we're looking at more here than just the evidence for the particle properties of electromagnetic waves. We are also looking for ways that photons can interact with matter. So this is very practical. When would this be practical? Well, what if you're, say, 30 feet below the surface of the ocean, and you have light coming in from the sun that has all kinds of different wavelengths? That light energy, depending on the energy of the photon, is going to interact with the water molecules in ways that will prevent all of that light from getting to you, say down at 30 feet below the surface. And so in a transparent medium, the attenuation of light is controlled by these different mechanisms that we're outlining here for you. And I won't outline all of them, but some of the major ones we'll be looking at. So photoelectric effect then would be associated with visible photons interacting with matter. And so then the electrons would absorb those photons. But what if the photon had, say, 10 or 100 times that energy? So if we had photons with 10, say, to 100 eV of kinetic energy, or of total energy, if the photons have much more than just a few eV, which was the case for the photoelectric effect, then we're talking about very high ultraviolet photons here, ones that are much higher in frequency and much shorter in wavelength. And so at this point, the electron can no longer absorb the photon. It's too big of a mouthful. We could affectionately think of this as being like force feeding a baby with a shovel. Okay? It's just not going to happen. And so if the electron can't absorb the photon, the electron scatters off of the photon elastically. And so that's called Compton scattering. So this is like an elastic collision between the photon and the electron. Why elastic? Why wouldn't some energy be lost during the photon-electron collision? Well, because the energy that's lost in that kind of a process normally, when we have, say, billiard balls colliding or whatever, is caused by friction. And we're below the level of friction. Friction is a molecular property of matter and not an atomic property of matter. And so if we're below the size scale at which friction is significant, then essentially all collisions are elastic collisions. So it's not so idealistic then in a subatomic physics context to think of subatomic particles as colliding elastically. And so if we look up at the data projector, we can see the kind of a process that we could imagine here. Here we've got this kind of symbolic representation of a photon, which has a typical wavelength associated with it, but only a finite length, just a little chunk of the electromagnetic radiation. That comes in, hits an electron, let's say here that is starting at rest, and causes the electron to recoil and the scattered photon to bounce off and go down to into the lower right-hand corner of the screen. Okay, so for that kind of a process, then we can think in terms of the conservation of energy and the conservation of momentum that is taking place in this kind of a problem. And so here's our photon moving along. Okay, so it's got an energy that's equal to hc over lambda. It's got a momentum that's equal to, well, the momentum here is, how can we get that? Well, it's E over c. How do we get that? Well, we go back to our Einstein triangle relationship. Remember that E squared is equal to P squared C squared plus M naught squared C to the fourth. And if we look at this from the standpoint of a photon, the rest mass of a photon is 0. So therefore, E is just equal to PC. And so you can review your notes on this. I went over this as a special case of the Einstein triangle relationship when we were in chapter 37. But rewriting this then as hc over lambda for the energy of a photon is equal to pc, we see that the momentum of a photon is just h over lambda. Okay, so a photon does in fact have momentum and can impart a force, because remember, force is dp dt. So if the momentum changes as a photon hits the electron, that is associated with a force being imparted to the electron, just like with a regular collision between two solid objects. Okay, and so the photon then has a momentum that's equal to h over lambda. It comes along, hits the electron, which is at rest, and then scatters the electron off at some angle phi. So the electron has some momentum now, which is the mass times the velocity of the electron. And the photon also has some energy. Okay? And so that energy is going to be equal to m naught c squared plus k, okay, where k is the kinetic energy of the electron. And then the photon is going to have a, now normally if the photon has given up some energy, then we would say, well, it's slowed down, right? If it's a regular particle. But photons can only go the speed of light. So the only way that the photon can lose energy, you can see here from hc over lambda, is to increase the wavelength. Okay, so we can call this lambda naught, and then the energy here is going to be hc over lambda prime, where lambda prime is the new longer wavelength, lambda prime greater than lambda naught. And so that's where the energy has gone. It's gone into giving the electron some kinetic energy. Okay, so that's going to be the new energy of the photon, and the new momentum is going to be h over lambda prime. And so if we call this angle here phi and this angle theta for the scattered angles of the photon and the electron after the oblique collision, then we can use conservation of energy, because no energy is lost during the collision. It's elastic. So the energy before then is going to be the energy of the photon, which is hc over lambda naught, plus the rest energy of the electron. The electron still has rest energy before the collision. That's m naught c squared. And then after the collision, the photon is going to have an energy hc over lambda prime, and the photon is going to have an energy, the electron is going to have an energy that's going to be m naught c squared plus k. Okay. Remember that the total energy of the electron, E, is equal to m naught divided by square root 1 minus v squared over c squared, or m naught c squared plus k. So here I'm writing this in terms of m naught c squared, because that is what I had the rest energy equal to before the collision between the photon and the electron. So the m naught c squareds cancel out, and so this gives me then the kinetic energy of the electron after the collision is going to be equal to hc over lambda naught minus hc over lambda prime. Or that's hc times 1 over lambda naught minus 1 over lambda prime. Okay, so that's our kinetic energy, but we also have conservation of momentum, and we've got two different equations for conservation of momentum. The sum of the x momenta before equals the sum of the x momenta after the collision. So if we define our xy axis like this, then before the collision, all we've got is h over lambda naught. There's no momentum for the electron before the collision. Then afterward, we've got this component of the momentum of the electron, which is going to be mv cosine phi, plus the x component of the momentum of the photon, which is going to be h over lambda prime cosine theta. Okay, so that's our x. So this is equation 1, we could call it here. This is equation 2 that satisfies the conservation of x component of momentum. And then we also have the initial y momentum equals the final y momentum. Okay, and since we've defined the x direction to be the initial direction of the momentum of the photon, that means that there is 0 y momentum before, and that means that there also has to be a total y momentum of 0 after the collision. So the x momenta add, but the y momenta cancel. Okay, so what we're going to have then for the y momenta is going to be here we've got the y momenta of the photon is minus h over lambda prime times the sine of theta. Plus, and then for the y component of momentum of the electron, we're going to have mv sine theta. Okay, so that's equation 3. Right, now, I could spend a half an hour working through the algebra of this, but it's done in your textbook. So I would certainly expect that you would be able to work with the kinetic energy expression just the way that it's been written here, because you can get it just by understanding how the energy relates before and after. But in terms of having to do the algebra, I probably wouldn't make you do that on a quiz. But the result is the following. We solve equations 1, 2, and 3 simultaneously. We get delta lambda, which is equal to lambda prime minus lambda naught, is equal to h divided by mass of the electron times c, times 1 minus the cosine of theta. Okay, so theta then is the scattering angle of the photon. So then the difference in the wavelength can also be used to help us figure out the kinetic energy of the electron after the collision. So let's try to work that through with an example. Let's say that the photon comes in, scatters off the electron like this. The electron goes off this way, and the photon goes straight down. Is that possible? Well, sure, that's possible. You could actually get the photon to bounce straight back. And so that would be the maximum amount of energy that you could impart to the electron, is if the photon bounced straight back. If it bounces off at a 90-degree angle, then theta would be 90, and we would have 1/2 of the maximum change in the wavelength associated with that kind of a process. So let's do that. Let's set theta for the scattering angle of the photon equal to 90 degrees. For this example, let's say that lambda naught is equal to, let's make this 10 to the minus 6 meters. Okay, so if we set lambda naught equal to 10 to the minus 6 meters for the photon, then it's going to have a little higher energy. Somewhere around 10 to the minus 7 would be in the low ultraviolet, and so this would be in the higher ultraviolet. So then we could get the delta lambda, the change in the wavelength, is equal to lambda prime minus lambda naught. It's equal to h. Okay, so that's 6.63 times 10 to the minus 34 joule seconds, divided by the mass of the electron, 9.1, 10 to the minus 31 kilograms, times c, 3 times 10 to the 8 meters per second, times 1 minus the cosine of 90 degrees. So that's just multiplied by 1. Okay, so that gives us delta lambda is equal to 2.42 times 10 to the minus 12. That would be meters. Okay, so we see then that the difference in the wavelength in this case is only on the order of maybe something like 2 millionths of the original wavelength. And yet, that's enough for us to now calculate the kinetic energy of the electron. Which we can get from equation 1 over here. This is our kinetic energy. And so we can write the kinetic energy of the electron then as hc times 1 over lambda naught, so that's 10 to the minus 6 meters. Actually, let's make that, I'm sorry, 10 to the minus 8. I want this to be smaller, not bigger than the wavelength of light. Okay, so if I make that 10 to the minus 8, then this is only 1/10,000th of the Okay, so this is ultraviolet. We go to smaller wavelengths to get higher energy. So somewhere around 3 or 4 times 10 to the minus 7 to 7 times 10 to the minus 7 is visible. So we'll make this ultraviolet photon. Okay, and so then we'll subtract from that 1 over lambda prime, which is 1 over 10 to the minus 8 plus 2.42 times 10 to the minus 12. Okay, which, if we want to write this out in this kind of a context, this would be out in the 4th decimal place. This would be 10.000242 is what we'd have there for the final wavelength. And that final wavelength is going to be bigger than the initial wavelength because that photon has lost energy in the final state. Since it's lost energy, its wavelength has gotten bigger. Not a lot bigger, only 1/10,000th bigger. But it's still enough to give the electron a reasonable amount of kinetic energy. Okay, and so remember that when you're subtracting like 1 over lambda naught minus 1 over lambda prime, that's not the same thing as 1 over lambda naught minus lambda prime. So you have to do the 1 overs separately and then subtract them, and that may seem like a very simple rudimentary thing to be saying, but I found that even people that have had lots of calculus tend to make that algebraic mistake. So just making sure you're not one of them. Okay, so here H, that's 6.63, excuse me, times 10 to the minus 34 joule seconds, times C, 3 times 10 to the 8 meters per second, times 1 over 10 to the minus 8 minus 1 over 1.000242 times 10 to the minus 8 meters. And so when we do that, we get that that gives us 4.81 times 10 to the negative 21. Joules. Or if we want to convert that to electron volts, can say we've got 1 eV for every 1.6 times 10 to the minus 19 joules. So that gives us 0.003 electron volts. So that's our kinetic energy, or if we wanted to, this clearly is a very low kinetic energy in relationship to the rest energy. Mass electron times c squared was 0.51 MeV. So we can immediately, by seeing that this is just a 3,000ths or a milli electron volt in terms of its kinetic energy, we can say that this is non-relativistic. It's a non-relativistic kinetic energy, and the electron is moving, but it's, we could figure it out then by just setting the velocity 1/2 mv squared equal to the kinetic energy, and we could figure out the velocity of that electron, but it wouldn't be a gigantic number. Okay, so I could ask you, well, what scattering angle would produce the highest energy electron? And so in order to get that, you would need to have the biggest difference between these two. And so that would mean that you'd need the biggest value for delta lambda down here in the denominator to get a bigger difference between these. And so that would tell us then that the biggest energy that could be imparted to the electron via Compton scattering would be to come in and then bounce straight back again. And I think it's intuitively reasonable because that would change the momentum of the photon by the largest amount and therefore impart the largest force to the electron during the collision. And that would produce the largest possible value for delta lambda, which would be double the value that I solved for over here, if the angle were 180 degrees. Now what if the angle were 0? Well, if the angle were 0, what would that tell us about the photon's interaction with the electron? There wouldn't be any, right? If theta is 0, it means that it didn't interact. So theta equals 0 is the same thing as saying the photon missed the electron. Didn't hit it at all. Okay? And if it misses the electron, then we have 1 minus cosine of 0 is 1. We get delta lambda is 0 because the photon didn't interact at all. It just missed it. Okay? And so that's your trivial example of the lowest possible energy is when it misses it, and that happens when theta equals 0 because there is no scattered angle for the photon. All right, so that then is what happens when we're at energies for the photon that are on the order of maybe 10 to 100 electron volts. Okay, now here I just gave you 10 to the minus 8 for the wavelength of the photon, and we know the visible light is somewhere between 4 times 10 to the minus 7 to 7 times 10 to the minus 7. So I just gave you something that was just a little bit higher than that in the lower part of the ultraviolet. But I could have made this wavelength 10 to the minus 9. Then it would be on the order of maybe 50 or 100 electron volts. Okay? And so then you would get a bigger value here for the delta lambda, and you get a bigger value for the kinetic energy. All right, next, for the third type of interaction between photons and matter, I'd like to look at something that is very high energy. For really high energy photons, you could either produce extremely high energy particles, but if you can get the energy high enough, let's even go beyond that, we can actually get energy can convert to matter. Say, well, how could you do that? Well, remember, E equals mc squared. So that was something that was a relativistic result. And so if these photons then have enough energy, we might be able to actually create particles out of the photons. Okay, so how could this be done? Well, there are a number of ways of creating matter out of photons. But let's look at a situation where we have a photon that's moving along, and if it has a high enough energy, let's say it produces 2 particles. Now, it turns out that these particles are going to have to be opposite in charge. And so we could think of this as being, for example, an electron and a positron. What's a positron? Well, it's just an electron with a positive charge, or an antimatter electron. Now, antimatter has the same properties as regular matter, but with opposite charge And although we haven't talked about spin yet, it also turns out that has to have opposite spin as well. Okay, and so the thing that's interesting about antimatter is that if you combine antimatter with regular matter, you get 100% conversion to energy. So this is actually one of the big unanswered questions in physics and cosmology is when matter is produced, for example, in the Big Bang, we should get equal amounts of antimatter. And yet, if that were the case, then the universe should have canceled out. There should have just been all of those electrons, all those positrons, all those protons, all those antiprotons. They should have just canceled. Or if there's still antimatter around, it should be combining with regular matter and producing huge explosions. None of that is being observed. So the big question then, one of the big questions in cosmology is, where's all the antimatter? One of the biggest unanswered questions in physics. So either we negate our own existence by saying that it all canceled out at the beginning, or we say that somehow it separated, but if it did, then there should be interactions between antimatter and regular matter that we should be able to observe. And they'd be huge explosions, because matter and antimatter have 100% conversion to energy. It's the ultimate energy source. And one day we'll be able to make antimatter in reasonable quantities. Right now, we can make something like maybe 5 grams of it every 60,000 years at the rate that we're able to make it. Unfortunately, it costs thousands of trillions of dollars to make that 5 grams. So although the technology is there to make it, we can't make it efficiently enough to use it as a power source yet. But in the future, that will probably all change, assuming that we last long enough to be able to do things like this. But that still doesn't answer the question of why we don't have a whole bunch of antimatter in the universe today. And one possible answer, although it hasn't been proven, is that there's a slight asymmetry in the laws of physics between how much matter and how much antimatter is produced. And the possible answer then is this asymmetry may cause something like 1 part in 100,000 more matter than antimatter was produced in the Big Bang. And so all but 1 part in a billion canceled. And what's left? The 2 trillion galaxies in our universe of today, in just the visible part of the known universe, which is probably much bigger than our light horizon would allow us to see. that 1 part in 100,000 is the whole observable universe. And everything else just canceled out and became energy right at the beginning of the universe. So that is what we're trying to show now, is that there is an asymmetry in some of the particle interactions that take place in the Large Hadron Collider in CERN. And so there are neutral kinds of particles that, in which like the K meson may produce an antiparticle that's also neutral, but with a slightly different amount. And they're trying to determine whether that's enough to account for all of the missing antimatter in the universe.